Yes, hello, good morning. Today we're going to talk about section 6.3 entitled Applications of Normal Distributions. As I mentioned, if I was going to write a book, I'd probably call this section Non-Standard Normal Distributions. In other words, there are many, infinitely many normal distributions, bell-shaped distributions. Some are tall and skinny, some are short and fat. Some may have the bell peak at higher values than others. So as we traverse up and down the number line, we can see normal distributions plotted everywhere along the number line. Now in 6.2, we talked about standard normal distributions where the mean was 0 and the standard deviation was 1. Well, in non-standard normal distributions, the mean may not be 0 or the standard deviation may not be 1. And we're going to learn today how to deal with that situation. Let's refresh our memories regarding section 6.2. Remember, we had studied the standard normal distribution. The standard normal always peaks at 0. And if you're interested in the probability of a standard normal random variable being between limits of interest, let's say a and b, we're basically looking for this area under the standard normal curve. So remember, we use the letter z to indicate a normal distribution with a mean of 0 and a standard deviation of 1. That kind of goes without saying by definition. And if we want the probability that z, for example, is between some values a and b, what we're doing is looking for this shaded area. This shaded area here is this probability, the area under the standard normal curve between a and b. Alright, so again, how about figuring out probabilities that are not standard normal distribution, non-standard normal distributions. Alright, well, the idea is somewhat the same. Let's see, let me go through an example here. Let me cite an example here. Let's say we've got, suppose, women's heights, adult women's heights are normally distributed. With a mean of 63.8 inches, that sounds about right, and a standard deviation of 2.6 inches. Alright, so 5 feet tall is 60 inches, so 63.8 inches, that's about 65 feet 4, that sounds about right. Alright, I'm going to take this information and summarize it like this. I'll say women's heights. I will signify with the variable x. Now, x will then represent the height of all adult women of all time, and we are claiming those heights are normally distributed with a mean not of 0 but of 63.8 inches and a standard deviation of 2.6 inches. Right? So this is my preferred notation for describing a non-standard normal distribution. Suppose I was to ask you this question. Let's randomly choose one adult woman, and find the probability that that adult woman has a height between 60 and 70 inches. That's a P there for probability. Let me make that a little clearer. Alright, let me give you an idea of pictorially what's going on here. We've got a non-standard normal distribution with a mean of 63.8 inches. So we're claiming if we plot the heights of all adult women, the heights will follow a bell-shaped or normal curve that will peak at 63.8 inches. Now remember that we're no longer dealing with a z variable here. This non-standard variable, I'm going to call it an x variable. All right, some women are tall, some women are short, but most women seem to be in the middle of the road within a neighborhood of 63.8 inches. So I think you'll agree. All right, how are we going to grind out this probability? Well, we want the probability that x is between 60 and 70 inches. Well, let's see. I'm going to ballpark right down, plot those values, 60 and 70. Give me a minute here. I want to erase carefully what I've written here. And I'm going to go to a different color. Try green. Alright, where does 60 inches land on our graph? I'll say it's here. And where does 70 inches land on our normal distribution? I'll say up here somewhere. So if I want the probability that a randomly selected woman's height is between 60 and 70 inches, I want the area under this distribution between the limits of 60 and 70, the boundaries of 60 and 70. Okay? This shaded area, I should have labeled that as 70. Please forgive me. Label that as 70. This shaded area stray mark here, hang on, is this probability. Okay? Now I suppose we could do two things. We could use integral calculus to grind out the area under this normal shaped curve, but of course calculus is not a prerequisite for this course. So we're going to let the calculator grind this out for us. We will still use the normal CDF command, much like we did in section 6.2. We'll use normal CDF. Right. Operator. Now let me write the full syntax here because I purposely didn't give you the whole picture in section 6.2. Remember the syntax. You got to put a left bound as your first parameter using the normal CDF command. Then a right bound, and that should be no surprise to us. But there are two optional commands. Let me go to a different color here. Two optional parameters, I should say, for this command. Let me get another color here. You can optionally put in a mean and a standard deviation. And I think you get the picture. If you don't put in a mean and a standard deviation in this command, of course the calculator assumes you're in a standard normal situation, as in 6.2. So what do you do when you're in a non-standard case? Well, you just enter in the non-standard mean and standard deviation. So let me write this down. If omitted, calculator assumes the mean equals 0 and the standard deviation equals 1. In other words, the standard case. Okay? Alright, so we can now easily grind out this area, easily grind out this probability using this command. So the probability that x is between 60 and 70, well, let's see, it would be normal CDF as before. We hit second distribution, normal CDF. Remember that from section 6.2. I'm going to plug in my left bound. Well, my left bound up here was 60, recall. My upper bound, my right bound, will be 70. And of course, my non-standard mean and standard deviation was 63.8 and 2.6. So kind of a long-winded command here. You've got 4 parameters to enter in. Well, I punch this out, and I get 0.92. So the probability that a randomly selected woman is between 60 and 70 inches, in other words 5 feet tall and 5 feet 10, is 0.92, or roughly 92%. of adult women's heights fall within that range, 60 and 70 inches. Alright, let's try another example of this type. Same information. Let's say again X. I'll let that be women's heights again. I claim that women's heights have a normal distribution. And when I say normal distribution, I'm going to ask myself two questions. What's the mean and what's the standard deviation? As before, the mean was 63.8 inches and the standard deviation for these women's heights was 2.6 inches. Alright, so now I'm going to say find the probability that a randomly selected woman's height is more than 70 inches. Now, there are a bunch of adult women that are taller than 70 inches. That's 5 feet 10 inches. Probably not many in the long scheme of things. Well, I'm going to translate this question into a mathematical statement. I really want the probability that X, a randomly selected woman, is greater than 70 inches, or that is a height greater than 70 inches. Pictorially, there's my distributions of women's heights. Some women are tall, some women are short. Most women are somewhere in the neighborhood of 63.8 inches. Now, what does greater than 70 mean? Well, since greater than 70 means to the right of 70 on this scale, so I'll put 70 up here, and the total area under this non-standard normal distribution between 70 and really positive infinity in theory will be our sought after result. Alright, so how am I going to grind this out? Well, recall you're going to need a left boundary and a right boundary to use your normal CDF command. So we have to fool the calculator a little bit. I'm going to write out normal CDF. Use your second distor button at the gold level above the vars button. Second distribution menu. Pick normal CDF. And I want to put a left bound. Well, clearly, my left bound here is going to be 70. Remember, you want this area under that non-standard normal curve. What's the upper bound going to be? Well, in theory, this goes off to infinity, so let me put infinity here. Well, I'm going to put, our author, as you recall, uses 999,999 kind of as a best approximation of infinity, so we'll take the author's lead on that, like we did in 6.2. And again, in the non-standard case, you've got to put in your non-standard mean and your non-standard standard deviation. Okay. Alright, so we punch this out, and we get a rather small value probability-wise, and that's what I probably would have expected. The probability then that a randomly selected woman has a height greater than 5 feet 10 inches or 70 inches is going to be, well, it's less than 1%. It's 0.008% and change. Alright, so remember, I think the idea here is to remember that this 999,999 is going to be our author's approximation of infinity. Alright, easy enough. Let's try another one. I want to look at an example, written out example in the book. This one is example 2 on page 261. And let me refresh our memory. Example 2, page 261. I'm going to read through the problem here. You might want to turn there also. The chapter problem stated that British Airways and many other airlines have a requirement that a member of the cabin crew must have a height between 62 inches and 73 inches. Given that men have normally distributed heights with a mean of 69.5 inches and a standard deviation of 2.4 inches, find the percentage of men who satisfy that height requirement. Alright, so let me write that down. We claim, or the author claims, that adult men have heights that are normally distributed with a mean of 69.5 inches and a standard deviation of 2.4 inches. Alright, that's a 5 there, believe it or not. Show it again. Alright. So we are really asking, what is the probability that a randomly selected man would have a height between the necessary limits for British Airways, namely between 62 and 73 inches. So we seek this, 62 and 73 inches. Alright? The probability that a randomly selected man has heights between 62 and 73. Whoops, I forgot an inequality symbol there. Hang on a minute. Redo that. Okay. 62 and 73. Pictorially, we are in a bell-shaped curve. Some men are tall, some men are short, most men's heights fall within a neighborhood of 69.5 inches or 5 feet 9.5 inches. Alright, we want the probability that a randomly selected man is between these two limits, 62 and 73 inches. Alright, well, on our graph, I'm going to put 62 down here, certainly left of the mean, and 73 I'll put up here, maybe exaggerating a bit for demonstration purposes. So what we seek, again, we make this connection between area under a curve and probability. Right? We want that area under this non-standard normal curve. Right, yes, we could use integral calculus if we desire, but again, calculus is not prerequisite for this course, so we'll let the calculator do it for us. And again, we'll use the normal CDF command. You hit your second button, get your distribution menu, dister. Normal CDF. 62 is my left bound. 73 is my right bound. And again, in the non-standard case, you've got to enter in your non-standard values for mean and standard deviation. Alright, so normal CDF, let me check it, 62, 73, 69.5, 2.4, and I punch it out, and I get 0.927. And that seems rather high in the world of probability. And I think, well, in your own personal experience, it would probably seem that most men are within 62 and 73 inches of height. Well, 62 is 5 feet 2 inches, 73 is 6 feet 1 inches, and yes, I would expect that approximately 93% of men fall within that range. That's not surprising to me. So I will conclude. I will say so 92.7% or 93% of adult men satisfy the British Airways requirement for height. Okay? Alright. Now we want to work the normal CDF command backwards. Oh good, let me get another screen here. Now we're going to work backwards. Okay. Up to now, we were, let's see, let me write that down. Up to now, in this section, we were given X scores, not Z scores, not standard scores, but X scores, non-standard normal scores, and we found probability. Probabilities. Now we want to work it in reverse. In other words, given probabilities, typically in the form of areas, we will want to find the corresponding X scores. Right? Much like we did in section 6.2. You recall we did this in 6.2 using the inverse normal command, or invnorm, and we're going to do the same thing here. Right? We'll use inv norm command. But again, here we're going to be in the non-standard situation. Let's cite another example in the book. Example 3. This is on page 263. And let me read it to refresh our memories. You might want to turn there also. When designing an environment, one common criterion is to use a design that accommodates 95% of the population. What aircraft ceiling height will allow 95% of men to stand without bumping their heads? That is, find the 95th percentile of heights of men, and assume the heights of men are normally distributed with a mean of 69.5 and a standard deviation of 2.4 as before. Alright, so again, I'm going to make this assumption that men's heights are normally distributed with a mean of, let me check it again, 69.5 inches, same as in the last example, and a standard deviation of 2.4 inches, right? So we're going to want to find the 95th percentile. Right? The book says, let me read it, and that's all it says, find the 95th percentile of heights of men. So find the 95th percentile. You may recall that's P sub 95 from earlier chapters. And it's really the score that cuts off the top 95% from the, the top 5% from the bottom 95%. Let me make that, write that down. As I'll say, it cuts off the top 5% from the bottom 95%. Okay, if you've scored in the 95th percentile, that means 95% of men's heights are less than yours, right? So again, let me give it to you pictorially. We've got a distribution of men's heights here. Right? Some men are very tall up here, some men are very short down here, but most men, it seems, fall in a neighborhood, within a neighborhood of 69.5 inches, in other words, near the mean. Alright, so I claim there is a score that cuts off the top 5% from the bottom 95%, and I'll say it's right here, right, for demonstration purposes. So that is the score I seek. It's an X score I seek. And again, I'm going to use inverse normal, like we did in section 6.2, but how are we going to use that inverse normal command? Well, if this area up here is 5%, represents 5% of all adult men, I claim that area under the standard, the non-standard normal, is 0.05, and then the area below that value is going to be 0.95. Remember, the total area under the any normal distribution is, of course, 1. Okay? So we're going to use the inverse norm command. Right? Well, remember, the syntax for your inverse normal command requires that you input your left area. Right? And of course, much like with the normal CDF command, if you're in the non-standard case, you must enter in your non-standard values for mean and standard deviation. Okay? Again, if you leave these out, if you leave these two out, the calculator assumes you're in a standard normal distribution. Okay? Alright, so that's the only thing that changes here, really. Well, for this problem, we'll say we're going to use inverse norm. Right, the area to the left of this value under that standard normal curve is going to be 0.95. And of course, we must use our non-standard values for mean and SD, namely 69.5 and 2.4. Alright, I punched this out. Inverse normal point, let me check it, 0.95, 69.5, 2.4 looks good. And we come out with a 73.4 inches. That is the 95th percentile. That is the value that separates the bottom 95% from the top 5% of all men's heights. Alright, so the long and short of it here is, if you the British Airways designs these planes with such a height, then 95% of men will not bump their heads on the ceiling of the plane. Okay? Let's try one more example. We'll call it a day. Example 4, page 264. Let's turn there and read. Alright, here we go. Some educators argue that all students are served better if they are separated into groups according to their abilities. Assume that students are to be separated into a group with IQ scores in the bottom 30%, a second group with IQ scores in the middle 40%, and a third group with IQ scores in the top 30%. Okay? The Wechsler Adult Intelligence Scale yields an IQ score obtained through a test, and the scores are normally distributed with a mean of 100 and a standard deviation of 15. Find the IQ scores that separate the three groups. Alright, let me write down the given information first. We're talking about IQ scores, and I'm going to let X represent that body of scores. X is a variable that represents all the IQ scores of all people of all time, and the claim is that those scores follow a normal distribution with a mean of 100 and a standard deviation of 15. Okay, that is the given information. Alright, we want to find the scores that separate the bottom 30%, the middle 40%, and the top 30%. Alright? So pictorially, I'm going to draw the distribution of all IQ scores of all time. We claim it's a normal distribution. The peak, most scores seems to fall within a mean of 100. And of course, some are high or some are low, but most are somewhere in between. Alright, if we want the X values that separate the bottom 30%, well, I claim, I'm going to write it here somewhere. Right? That's one of the scores I need. Well, because then the probability of being less than that score is going to be 30% or 0.3. Right? So the area below this value is going to be 0.3, right, under this non-standard normal curve. Alright, we want to then isolate the middle 40%. Well, I'll put another value up here. Now, I want the probability of being in this middle range to be 0.4. I may be exaggerating for demonstration purposes. And this score will also, of course, then cut off the top 30%, so that top area, that right area under the non-standard normal curve will, of course, be 0.3. Alright, so we're looking for two values here, here and here. And of course, we can use our inverse normal command if we play our cards right. Alright, so let me call this value x1, And let me call this value x2. X sub 2, so we don't get confused. Alright, so x1, to find the x sub 1, we're going to use our inverse normal command. Alright, the area under the non-standard normal curve to the left of this value is, of course, 0.3. So my left area is going to be 0.3. And, of course, my mean and standard deviation in this non-standard case is 115. 100, 15. Alright, if I punch this out, I get x1 equals 92.13, and that makes sense. Let me label this here, 92.13. It's certainly left of 100, so it's consistent with our diagram here. Alright, so x sub 2 should be above 100. Let's try it. X sub 2 is going to be inverse normal. Again, you get there to your through your distribution menu, hit that second gold button and the distor command above the vars button, right? Inverse normal command, and you want the area to the left. Now the area, be careful here, the area to the left of this x2 value is going to be 0.4 plus 0.3, that's 0.7. Right? So I can hit inverse normal 0.7, comma 100, comma 15, and I'll punch it out. So x sub 2 is going to be 107.9, and that looks about right. Certainly it's more than 100. Certainly it's on the correct side of the mean, as we would expect from the diagram. Alright, so there's our motif for how to handle non-standard normal distributions, and we'll call it a day. This concludes section 6.3, applications of normal distributions.